Physics dudes, let's get this party started with some me solving out some problems for you. Here's what I'm going to do. I'm going to show you folks the way that I go about solving problems. And I'm going to show you the same exact techniques, the same exact process. And it might be a little bit more confusing on the easy problems that are easy to solve. The point that I'm trying to get is if you do the technique that I'm showing you now, then you'll be able to almost solve any of these problems by going through the same exact steps. And sometimes that's really helpful to students to be able to kind of have this these steps that they have to follow, this formula that they go through. Okay? Now, I'll be honest with you, it's kind of like in algebra. Do you remember the quadratic equation? Okay. And Ethan, I'm going to need you to respond back to me a lot. Oh, and Caitlin. Oh, awesome. Caitlin, what's going on? All right. Do you guys remember the quadratic equation? And I feel like I was your teacher for some of these, so maybe hopefully you memorized it really good. Okay. I always called the quadratic equation like my bazooka. And it would be like the thing I would use, the hand grenade that I would use to kill the fly. Where it will always work. It might not be elegant. It might not be pretty, but it will work. Well, that's kind of what I'm going about with this thing. I'm going to show you these steps, and as I get through this, you're going to start internalizing these steps so much so that you'll be able to do them without really thinking about them, and then you'll probably be able to cut out my system. But for now, stick with me with this system. First of all, okay, all right, I just want to make sure that ended up backwards because I'm going to go on the other side of the screen and do some example problems for you. Okay, I am the monkey behind the glass again. At the airport, an airplane comes to rest at a very long runway and must attain takeoff speeds before reaching the other end of the runway. Okay, so what I want to do is find what is the minimum length of runway if the plane has an acceleration. So, all right. So at an airport, I got a plane. And here's my plane. I don't know why it looks so ugly. You don't need to be a great artist in physics. You just need to draw lots of pictures. All right. So I've got a runway, and what I want to do is I want to find the minimum distance I need to go in order, if I had an acceleration of 2.20 meters per second squared and a velocity final of 95 meters per second. Meters per second. All right. How long of a runway would I need? Okay. First thing I want you to do is I'm going to put up all of the 4 equations that I've told you to write down. I hope that what you did was you wrote this down on an index card or something like that, and you have it posted up right in front of your desk wherever you study. And that way, whenever you do your homework, you can just go look up there and cheat off of it. I'm fine with that. Write this down. And if not, then do that. So let's see. It was V is equal to V initial plus AT. That's the first one. Delta X equals 1/2 V initial plus V final times time. Delta X equals V naught T plus 1/2 AT squared. That's my personal favorite. And also V final squared equals V initial squared plus 2A delta X. Are we cool with that? Now, I talked a little bit about how I go about choosing which equation to use, and let's talk about that. So, the first thing I do is I draw out a picture and I write down all of the information they gave me in the question. Do you guys understand what's going on here? You got a jet that needs to get to a certain speed in order to take off. In order to do that, it needs to have a certain amount of runway. The jet can accelerate at 2.20 meters per second. The speed that it has to get to is 95 meters per second. Are we cool with that? And then I have my 4 equations that I'm going to keep up on the side of the board over here. All right. So I'm going to list out, there's going to be 5 variables in all of these equations, in all of these problems that you're going to solve. There's going to be 5 things that are, there's going to be 5 things. 3 of those things will be given to you. 1 of those things you'll be looking for. And the last thing will be our DKDC. Do you guys remember what DKDC is? I don't know if you guys were here for the last lecture. Okay. All right. So 3 will be given. 1 will be what we don't know. So I'm going to put a little question mark there. Cool? And the last one will be DKDC. See, this one is just DK, but this one is DKDC. And what I mean by that, and this is something I made up, is don't know, don't care. Got it? So 3 of these things will be something we know. 1 of these things will be something we don't know, and we want to find out. So I guess this would be called the DKC, don't know but I care. And then this one of them will be my don't know, don't care. I don't know it, nor do I care, find it. Cool? What are those 5 things that we're going to have? Well, you have velocity initial, you have velocity final, you can have an acceleration, you could have a time, and you could have a delta x. In this case, it's a delta x. This could also change to a delta y, depending, of course, on which direction we're going in. In this case, we're going horizontal, so I'm going to leave it as delta x. Are we cool with that? By the way, in all of these equations, you can change out the x for a y if you're talking about a vertical direction here. But since we're talking about something going horizontal, I'm going to leave it as delta x. So my question is, what is your velocity final? Well, we already know that. That's listed on the board. It's 95 meters per second. We cool? And your acceleration is 2.2 meters per second squared. What is your delta x? I'll make it easier. I'll draw something on our picture. What is your delta x? The distance, well, the length of the runway, but what's the number that I should put there? That's my question. Here. Well, I'm glad you're not sure. In fact, that's kind of the point, is that's our don't know. But we care about it because that's what the question was asking for, is what is the length of the runway? We don't know it. We don't know what to put for a number there, but we do care about it, so I'm going to put a question mark there. Okay. Now remember what I told you. There were 3 things that we would know. There was 1 thing that we won't know, and there is 1 thing that we don't know and don't care about. I see 2 things that we guaranteed I know. Check and check. There's going to be a 3rd one that I do know, and maybe I didn't give you this information right off the bat. Or maybe I didn't tell you this information in a number, I just told you and I want your logic to figure it out. What is the velocity initial? Ah, there we go. Yes, technically I did tell you that. Although I didn't say the word zero anywhere. But when I told you the question, I said, a plane starts from rest, accelerates up to 95 meters per second at an acceleration of 2.20 meters per second squared. By saying starts from rest, you can assume that rest means not moving, which means velocity initial is zero. So even though I technically didn't tell you that, I did tell you that. You guys see what I'm getting at here? All right, so this makes the time as what? It makes your time your dk/dc. I don't know about it, nor do I care about it. I have no information about my time, nor were they asking for it. So I don't even care about it. Got it? No, it's not going to be zero. Because, Kaylin, if you think about this, you're saying that in order to get from 0 to 95 meters per second, it's going to do it in 0 seconds? No, that's not true. It's going to be some number. In fact, if you wanted to, you could solve for that number. You could figure out what it is. No, and I would be careful with saying that too. But I would just leave it as, that's my don't know, don't care. I don't know it, I don't care. But this tells me I use this information to help me choose which equation to use. So I have 4 equations. And I want you to notice something in those 4 equations. In each of these equations, there are 4 out of the 5 variables that I have listed. Right? Which means they're missing one piece of information. In the first equation, it's actually missing your delta x. There's no delta x in this first equation. In the third equation, I'm just choosing random, it's missing your v final. Look at the third equation, there is no v final. So, knowing that information, which equation would you choose? 1, 2, 3, 4, or 4 to solve this problem? Okay. Ethan says 1. What about you, Kaylin? Just throw out a number. Or if you don't know, say IDK. My question is, in order to help me solve the problem, which equation should I start off with? The first, second, third, or fourth? Three. Okay. All right. You guys are both wrong, but let me explain this to you. I would advise you from using either 1 or 3, because if you look at equation 1 and equation 3, they have t in them. No, it's not 2 either. So obviously it's the fourth one. But if you look at equation 1, 2, and 3, they all have t in them. And if my time is my don't know, don't care, then why would I want to use an equation that has t in it? You see what I'm getting at here? So, I'm going to use the fourth equation. V final squared equals V initial squared plus 2a delta x. Now, just to keep in mind, you guys understand that the delta x, that comes as one thing, right? That's not a delta and an x. That's not 2 separate symbols. Okay, good. So I'm going to solve for delta x, right? What I like doing is, I don't like plugging in numbers, but I do like plugging in one number, is I always like plugging in zeros. So this is 0 right here. Right? V initial squared is 0, because 0 squared is still 0. So my equation is V final squared is equal to 2a delta x. Well, shoot, if you wanted me to solve for delta x, that's pretty easy. Are we happy with that? So delta x is equal to V final squared over 2a. Okay, let's think about this. let's do some analysis on this. Your V final, or I'll tell you what, let's look at the units. So this is my answer. What's the measurement? What is the units of V final? $95. No, that's the number. What is the units? Meters per second. Perfect. But I'm dealing with the meters per second squared, right? Or not meters per second squared. I'm dealing with a meters squared per second squared, because I need to take the meters per second and square the whole damn thing. We cool with that? What's the units for the number 2? There's nope. There is none. There's no units on the number 2. It's just the number 2. I'm looking at just the units. Right? All right, so what's the units on A? Meters per, all close. Meters per second squared. Now, be very careful, because the way I said it sounds exactly the same, and that's why you need to be very careful with writing it. This was meters per second, as in V final, squared, and this is meters per second squared. Yeah, it could get confusing like that. But do you understand how I got this? I'm just looking at the units. I don't care about the numbers. Kaylin, are we good? Do you understand how I tricked you with that 2 being unitless? Yeah, it's just a 2. All right. I got a fraction over a fraction. I'm going to make that meters squared per second squared times second squared over meters. I just take the fraction on the bottom, I flip him upside down, and I multiply it. Now what I'm going to do is I'm going to cancel out this second squared with this second squared, and then cancel out one of these meters on the top with one of these meters on the bottom. My answer, the units for my answer is meters. That's saying that if I plug in my numbers, the units will be in meters. Is that a good thing? Yes, because I'm measuring a delta x. I'm trying to figure out what x will give me that answer. And a delta x is measured in meters, so I better get a units of, so this right-hand side better have units of meters, even if it doesn't look like it right off the bat. You see what I'm saying? So now I could plug in some numbers if I wanted to, and I would plug in 95 meters per second, square that whole thing, divided by 2 times 2.20 meters per second squared. If you use your handy dandy calculator, I believe you'll get 2050 meters as your answer. And that's your answer, 2,050 meters. So how long is a runway? 2 kilometers, 2.25 kilometers. No, wait, is that 2.25? No. 2.05 kilometers. Pretty long. Are we cool with that? This wasn't a hard problem. It was kind of just a plug and chug. But again, like I said, there's a technique that you have to follow here where you have to go through certain steps, and you have to go through them systematically. You have to do each of these steps, and after a while, you'll get the hang of these things. I'll be honest with you, I don't think I've never really met any other physics teachers who teach you how to choose which equation to use and all of that kind of stuff. It's kind of a creative thing. All right, I'm going to erase this if that's all right. I'm recording this so you can always watch the archives. I'm going to erase these, but I'm going to keep those equations up on top. All right, let's do this. Delta x. All right, here's an important one. This is a good one. All right, let's do this one then. We're going to switch up the problem. In fact, I want to do a lab on this one. This one would be a good lab to do. You have a park ranger who's driving in the backcountry roads on Kauai. Let's say on Lanai, because my dad goes deer hunting on Lanai. And the problem is there was a deer that just kind of popped out in the middle of the road. Are we cool? And you jump on your brakes and you decelerate. Your initial velocity of your car will make this your car. Your initial velocity was 11.4 meters per second. We cool? Your brakes can decelerate at 3.80 meters per second squared. All right, do you guys see that? Okay. And I guess the question is, how long does it take for your vehicle to stop? Okay. What is your V initial? $11.4. Perfect. You're reading my mind. What's your V final? Don't know? Don't care? No, you know it. Let me ask you the question again. How long does it take for your vehicle to stop? How long does it take for your vehicle to stop? If your vehicle is stopping, then what is your velocity when you're stopped? Zero. You see how that's one of those questions where I did tell you the answer. I told you that information. I just didn't give it to you as a number. I'm a jerk like that. Physics is going to be a punk like that. I'm just letting you know. Okay, what is your acceleration? This one could be tricky as well. What is your acceleration? Come on, you guys. Are you guys not answering because I told you it could be tricky? Oh, by the way, I'm sorry. That's a 3.80. Okay. Kaylin, I love that you're saying 380 or 3.80. You couldn't maybe see that dot on the chalkboard. But it's wrong. It's actually negative 3.80. There's two words that I used that kind of gave you a hint. First, well, there's one word that I used that gave you a hint. First was you're decelerating. You're anti-accelerating. You're slowing down. So your acceleration is going to be negative. The thing that I use to make my life easier is I kind of gave you a hint by drawing this squiggly arrow going backwards for my A. So my V was going this way, but my A, and I always draw my accelerations with a squiggly line, is going that way, backwards. In order to kind of make sure that I'm keeping track of all of this stuff correctly, what I always do, and this is really important is I put in a coordinate system. I tell myself that everything going to the right is positive x, and everything going up is positive y. So I can obviously see that the acceleration over here, even though acceleration, I wrote on the board, acceleration equals 3.8 meters per second squared, it's actually negative 3.8 meters per second squared. Because this squiggly arrow goes in the opposite direction out of the positive x direction. Does that make sense? All right. What is my time? My dk. Yeah, it's my question mark. You can see that right out in the picture. That makes my delta x what? My dk/dc. There we go. In that case, with that knowledge in mind, which of these four equations would you choose? 1, 2, 3, or 4? Number 1. Great, because number 1 does not have any information about delta x. Good. So let's write down number 1. V is equal to V naught plus AT. Now, I don't like plugging in my numbers right off the bat. You're going to find that a lot of engineers, and even you'll want to plug in these numbers really quickly and then solve for the variable. I hate that. Do it my way for now. But remember, we're solving for t. I don't plug in numbers. There is a number I do plug in, though. If a number is 0 anywhere, I'll plug that in right off the bat. So this number right here, v final, that's 0. We cool? Now I'm going to do some algebra here, and hopefully it doesn't freak you out too much. Okay, what did I do? Just there. I took this velocity initial over to the other side, right? Yeah. And then I divided both sides by a. Yeah, okay, good. There's something freaky going on here. Remember, I'm looking for a time, and isn't my time going to be negative? Look at this equation. There's no such thing as negative time. What happens? How does that work? Switch it? Ah, yes, Kaylin, I think I know what you're talking about. I think what you're saying to yourself is, yes, Mr. Dalday, there is a negative out there, but you forget that that A is a negative number. So when you plug in the numbers, you're going to have negative 11.4 divided by negative 3.80, giving you a positive time, which is a good thing. If your answer comes out to be a negative time, you're wrong. I'll let you know that right now. Is that kind of what was going through your head, Kaylin? All right, before I plug in the numbers, though, let me just double check the units. So, the units on velocity initial, or what is the units on the negative? What is the units on the negative? Nope, the units on the negative is nothing. There are no units on just the negative. What are the units on the velocity initial? Meters per second. I agree with you. But it's almost like I was trying to trick you and say, what's the units on the -1? Because you can kind of think of that negative as -1. It's a number. It doesn't have units. All right. And then we also have the divided by A, so then you have divided by meters per second squared on the bottom. You take this fraction on the bottom, you flip them over, so then that's equal to meters per second times seconds squared over meters. Are we cool with that? If I start canceling out units, we got a meters here and meters here, seconds, go with that, seconds. And your answer is in seconds. Is that a good thing? Absolutely, it's a good thing because we're trying to measure time here. I'd want my time to have units of seconds. Exactly. So I know that I'm on the right track. Checking your units is a good way to see whether or not you got close to the right answer. If your answer came out where you don't get a measurement of seconds, then you'll say, wait a second, what the heck did I just do? I must have screwed something up. All right, now we can plug in the numbers, and I'm much more comfortable with plugging the numbers now because I know my units work out. Like I said, the negative 11.4 divided by negative 3.80 is equal to positive 3 seconds. So apparently it takes this guy 3 seconds to come to a complete stop. Are we cool with that? All right. Can I do one more problem with you guys? I don't know. I must be out of time by now, but is it right if I do one more? All right, cool. Well, what do you think about this? It's not too hard. All right. I think that when you try it out for yourself, you're going to realize that, this does take a lot of practice. And don't worry, I give you lots of practice. Yes, I agree, Kaylin. You're going to have so much fun finding all kinds of crazy sign errors that you make. And what I mean by sign errors is you'll forget to add a negative when you move this over to this side. And then you'll do the whole problem and you'll realize your answer's, like off. It's like you'll get negative time. And then you'll wonder, what the heck? And then you'll have to go back and look at your homework and say, oh, I screwed that up. Yeah, that was my bad, And then you go back and so you're going to find that you're going to mess up the negative signs a lot. I'm just letting you know now. You know what I mean? Maybe that might get you to pay attention to that, and then you'll avoid that mistake altogether. But I have a feeling you will make that mistake a lot, and you'll learn. So if you don't listen to me tell you you're going to have trouble with negative signs, then you'll figure it out. I guarantee it. Got it? You'll also find, for some reason, I always drop 2s. The number 2. I don't know why. I always, when I divide by 2, I forget to write it on one thing, and then it screws me all up. Yeah. Anyway. All right. Let's try this one, because this one looks like a good one. We have a speeder. Let's see. Okay, let's see. All right, here we go. So we got a police car. Police. I'm going to put a little siren on top. Okay? Here's my police car. And he sees he's sitting there eating his donuts. Here's Mr. Policeman with the donut. and he sees a car zoom by, pew, at a speed of 17.9 meters per second. So you got a car. Let's make it like a Lamborghini or something like that. The velocity of the car is 17.9 meters per second. And the police car has an initial velocity of 0. Got it? Now, as soon as the car passes, the police car starts up, and he starts going at an acceleration. So I should draw a little squiggly line and call it AP equals 4.51 meters per second squared. Okay. So I guess the question that I have to ask is, at what time will the police car catch this car? You guys get the problem? This dude's hanging out, he's at rest. Initial velocity 0. As soon as that car passes, he hits his gas. And the police car goes from a slow speed, and it slowly increases with an acceleration of 4.51 meters per second squared. This guy does not accelerate. This guy stays at a constant 17.9 meters per second. So if I were to draw the graph, and I'm going to draw this and erase it, so write this down. If I were to draw the graph, then this would be the position time graph of this equation, or of these people. So the race car will look like this. At some time, he's going to be a certain distance away. At some other time, he's going to be, a little bit further away, but it's going to be linear in nature. You guys see what I'm saying? This is for the race car. For the police car, he's going to be at 0 at time 0. And at 1 second later, he's not going to be much further. At 2 seconds, he's going to be even further. And at 3 seconds, he's going to be getting faster and faster and faster. So his position time graph will look somewhat parabolic in nature. Do you see that? So at some point, at some time, t equals what? They will meet up. And then the police officer will shoot the guy who's speeding, and then that's that. How's that? We're cool? All right. So I'm going to erase this. And notice how I have subscripts over here. This is my AP as an acceleration of police. This will be my V of car. So let's see. Let me show you how I would solve this problem. This problem would be like advanced, because there's this middle step that we're going to have to take. I know what you guys are thinking. I know you guys are thinking to yourself, well, one of the things you're thinking is, let me solve this problem. I'll show you how to do it. I'm going to ask less questions. I'm just going to go through it as best as I can. You ready? For the car, I'm going to list out the 5 things. I have my V naught. I have my V final. I have my acceleration of the car. I have my time, and I have my delta x of the car. Oddly enough, well, not oddly enough, it's actually pretty straightforward. I don't really care about the final velocity. So the equation I would use is probably going to be number 3. Delta x of my car is equal to my velocity initial times the time plus 1/2 a t squared. Now this is for the car I'm talking about specifically, right? But what is my acceleration of the car? I'm just curious to know. It's 0. So 1/2 times 0 times t squared is still 0. Not worried about that. We cool with that? Now let's look at the police officer. Velocity initial, I know. Velocity final, I don't really care how fast he was moving when he caught the guy. The acceleration of the police officer, I know. My time I'm looking for, and my delta x of my police officer. How far did the police officer travel? I don't really know that information. But oddly enough, I do care about this. And I hate to say this, but maybe the best way for you to really know which equation to solve for and what thing to solve for is just experience. You're just going to have to play with this until you figure it out. The equation I would use, again, if I don't care about the final velocity, is delta x of the police officer is equal to v naught of the police officer times time plus 1/2 AP t squared. Did I lose you? Okay. What's the initial velocity of the... And notice that I put little p's on all of these things right here. Because I'm talking about the police officer. Yes, exactly. And I didn't put a p on the times. Because there's no sense in doing that, because 1 second, 2 second, 3 second for the police officer is same as 1 second, 2 second, 3 second for the car. No, they both have the same time. They're both counting at the exact same times, right? Their clocks aren't messed up. This is, of course, we're assuming that we're not going at speeds close to the speed of light, and we have to take into account Einstein's theory of relativity. Don't worry, we won't get there. But I'm just saying, you know, according to this physics, this makes sense. All right. The initial velocity of the police car is what, again? 0. Good. So essentially my equation for my police officer is this. Are we cool with that? So what I'm saying here is this is the position of my car at any given time. And here's the position of my police officer at any given time. Now, at a very specific time, they meet up. And if they were to meet up, one piece of insight that hopefully you would be able to get, maybe just out of being creative and whatnot, is to say that delta xc is equal to delta xp. Why does that make sense? Or does that make sense to you? No, they're not both 0. That's not true. There we go. Because I said when they both meet. Well, when they meet, would you agree that their position will be the same? If they're meet, that means they are at the exact same position. That's kind of how it's defined. So I can say that, well, I can figure out what time it is because I know that my delta xc is equal to my delta xp. So I'm going to plug in what I have for delta xc is velocity of the car times time. I should probably put that as velocity of the car. And then this is equal to 1/2 a pt squared. Are we cool with that? Okay. This is a mathy thing right here. I need to solve for t. I can cancel out one of these t's. Do you guys agree with that? Now, in Algebra 2, maybe I didn't show you this, maybe I did. Maybe this is a trigonometry thing or an Algebra 3 thing. But when you cancel out a t and a t squared over here, you have to write down, don't forget t equal to 0. Because if t equals to 0, then that could be a solution. Because velocity of the car times 0 is equal to 1/2 acceleration of the police officer times 0. We'll talk about that in just a second. But let's solve for t over here. 2vc is equal to ap times t. T is equal to 2vc over ap. Are we cool? Oh, I'm sorry. Don't forget t is equal to 0. That's what it says. All right. We can check the units on this. Does it give you a good unit for time? I want you to do that. I'm not going to do that for you. You just tell me yes or no. I've done 4 of these already for you to check the units, of course. If you don't want to do it, just say I don't know and I can move on. All right, good, good, awesome. So I'm allowed to plug in numbers at this point. So I have t is equal to 2 times 11, or no, sorry, 17.9 meters per second divided by 4.51 meters per second squared. And that gives me 7.94 seconds. So apparently almost 8 seconds after the cop chased the race car, he caught him. Are we cool? Now, why are there 2 answers? There's 2 answers. There's time equals 8 seconds, and there's also time equals 0. The reason being is because the stipulation that you're placing on this is you're saying, when do these guys have the same position? When are they in line with each other? Well, one would be at some later time, 8 seconds later, this guy caught up with this guy. But also at 0 meters, remember I told you at 0 meters, this guy passed that guy. And that is another time in which they were at the same position. So the math said, hey, don't forget, that's a part of the problem too. I love how smart the math is. It almost tells you, gets you guys answers that you guys didn't think about. I think that the trick here is, the trick with this one is, when you guys see this problem, you wouldn't have thought to keep your delta x. Because I didn't ask you anything about the distance that they traveled in order to catch each other, right? All right, let me answer this and let my wife know. I'll call her back in 5 minutes. Hello? Can I call you back in 5 minutes? I'm in the class. All right, correct. All right. So what I'm saying is, when looking at this problem, you wouldn't have thought to keep around this delta x. Because what happens is you would think that that's your don't know, don't care. I didn't ask you anything about delta x. I asked you about the time, right? But actually, well, it does matter because there is that trick that you can think of that like when they meet up, I know that they'll have the same position. And so now all of a sudden, delta x has become relevant in your intermediate setup of the problem. Because you notice here that we got rid of delta x once we set it equal to each other, and then we substitute in what delta x for the car is and the delta x for the police officer is. We just said that that's VC times T, and that's 1/2 APT squared. There is no delta x in this equation right here. So it's almost like we deemed it important for half of the problem, and then we got rid of it. Because it still is our don't know, don't care, actually. I didn't ask you what the delta x was. I didn't ask you, well, I guess I didn't ask you two questions. I didn't ask you how fast they were moving, and I didn't ask you how far did they go when he finally caught up with them. You guys see? The only other piece that I want to warn you against is, what happens if one of these numbers wasn't 0? Like, there was a 0 here and a 0 there. Well, what's going to happen is, we had to solve this thing right here. The VC times T is equal to 1/2 AT squared. Okay? What happens if there was some number like 5 tacked onto the end of that? And you can get that by saying that, well, what if VP, the velocity of the police, wasn't 0? Or what if the velocity, or the acceleration of the car wasn't 0? Okay? What's going to happen when we have a problem like that? How do I solve for T in that particular case? Do you know how to solve for T here? All right, I'll show you. There we go. I think I know which equation you're talking about. I'm going to write this as 1/2 APT squared minus V naught T plus 5 equals 0. All I did was I took the V naught and I put them on the other side. When I subtract V naught T from both sides, it puts a negative V naught T on one side and it puts a 0 on the other side. Hey, guess what? That looks like an equation I showed you back in Algebra 2. That looks like the quadratic equation, but you switched out the x's for t's. And your A is a 1/2 A naught, or 1/2 A police, and then your B is negative V naught, and your C is 5. Well, in that case, in order to solve for T in this situation, you would just use the quadratic equation. Negative B plus or minus the square root of B squared minus 4AC all over 2A. Are we cool? I'm just showing you that because I'm warning you that some of these problems, the next step that I'm going to do is I'm going to just say, solve for T, and then you say, oh, shoot, I don't know how to solve for T. And then I say, well, do you remember the quadratic equation? So, dust off some cobwebs on that good old quadratic equation. See if you can remember it. Thanks for hanging out with me. I hope that made a lot of sense. All right, have fun. Do a lot of problems. Do a lot of homework. I give you a lot of homework because it's important for you to get good at this stuff. All right, take care.